Hi, I'm Mike Fairborn, Chief Meteorologist here at WCCO TV. Energy for Everyone, about energy and physics, is the 9th natural science series that we produced here in the Weather Center. Energy is universal. It's all around us. Living things run on it. We're alive because of it. Put simply, energy is the capacity to do work. Now, for those of you following along with an Energy for Everyone worksheet, here's how that works. At the start of each story, I'll present the topic. Then watch and listen for the main points. Make some notes. At the end of the story, you'll see a list of answers that you can write on the worksheet. There are 4 main types of energy we get directly from the sun, the source of all the energy on the earth. In our first story, we find out what they are. The start of another day. We take it for granted. But every day, the sun radiates energy. Particle waves that reach the earth as X-rays, ultraviolet and infrared radiation, radio signals, and visible light.
Here comes the sun, I say it's all right.
The sun, the star in our solar system, near the edge of the Milky Way galaxy, is a boiling nuclear reactor of hydrogen and helium. It radiates lots of energy, 52,000 watts for every square inch. When that energy reaches the Earth, 93 million miles away, it can be used by living things. Plants turn sunlight into chemical energy by photosynthesis, building with light. Humans through the ages have honored the sun for its life-giving energy. Visible light is a tiny part of the sun's energy. In the infrared wavelengths, we also get heat energy. You can measure it with a simple experiment.
I've got a solar heat collector, and inside I have a black panel, and while they're in here, the sun is shining on them, and they're heating up. And as they're heating up, they're giving off heat, and it tells me on the thermometer how much heat's giving off.
About 1,200 watts of energy fall on every square meter of the Earth's surface. Differences in heat absorption between the equator and the poles, along with the Earth's rotation, make the atmosphere swirl. This creates wind, another form of energy from the sun. When the sun's rays heat water, molecules at the surface get warm enough to move from liquid form to gas. That's evaporation, which lifts water vapor upward. When it precipitates out and runs downhill in rivers, humans can use it. It's an elemental form of stored solar energy. Scientists estimate that every day about 1,200 watts of energy from the sun strike every square meter of the Earth's surface. The worksheet assignment is to name 4 types of energy we get directly from the sun. The answers are light, which we see every day, of course, heat from the infrared band of sunlight, wind from heating differences on the Earth's surface, and evaporation, which happens as the sun warms our planet. Humans harnessed the energy in running water thousands of years ago. Minneapolis itself grew at St. Anthony Falls because of the water energy there. We also get energy from the sun indirectly. It's energy that's stored every day, a process that's gone on for millions of years. Where and how? Well, our treasure hunt begins with members of the plant kingdom. Plants are nature's way of storing solar energy. They capture the sunlight, use it to grow, and store it. Year in and year out, trees lock up the sun's energy, building up the topsoil, supporting a diversity of life in their forests. 500,000 years ago, humans discovered fire. They found they could burn the sun's energy out of plants and use it to cook food. Until just 200 years ago, firewood was our main store of energy.
First it was just our own muscle power, and then it was animal muscle power driven by foods, and then it was the first industrial revolution was water power and wood energy, both of which are renewable resources. It wasn't until coal began to dominate that we switched to a fossil fuel.
Coal is a black rock that's mostly fossils, old plants pressed hard. It's a fuel as old as dinosaurs.
This is a triceratops, about 150 million years old. Now, how many of you have heard of fossil fuels? Okay, all right. Do you know what we use fossil fuels for?
Cars.
Cars, and what else?
Lights.
During the age of dinosaurs, swampy forests covered lots of North America. So the United States has the Earth's largest coal deposits. But Minnesota doesn't have any. We buy our coal from other states. In the 1920s, another fossil fuel took the place of coal: petroleum, oil. The Coke refinery in Pine Bend distills it into the fuels we use to run our cars and factories.
The oil and the gas and the jet fuel that we burn in our society are stored solar energy that have accumulated over the last several 100 million years. In basically my lifetime, we are going to burn up about 80% of all of the oil that was ever in North America to burn. So in a very short time span, we're going to use up this bank account of stored solar energy in the form of petroleum.
The supply of fossil fuels is finite. Plants stored only so much, and each barrel of oil we use makes the next one more expensive and harder to find. The worksheet assignment is to name the plant products we burn that are stores of energy from the sun. They are wood, the first energy source people burned; coal, the primary fuel of last century; oil, which runs our society this century; and natural gas, which heats 60% of the homes in Minnesota. Now, our last two stories have focused on the direct and indirect stored energy that we get from the sun. Now we look at how we use this energy. Before the age of fossil fuels, people's wealth was counted by the number of horses that they owned. In ancient Egypt, only a pharaoh was rich enough to have 350 horses. Today, most Americans do.
You've got some slow traffic up Highway 36.
Each morning,
right now.
most Americans get in a 2-ton chariot, turn the key, and put 100 horses to work. And we don't even have to feed them much. The fabulous amounts of solar energy stored in fossil fuels made the workhorse a thing of the past. In 1956, we Americans drilled 16,000 oil wells, the most ever, producing enough energy from petroleum to live it up. Every year, cars got bigger and heavier and used more energy. We built suburbs and drove alone to work. We built shopping malls that you'd only go to in a car. And since energy was priced at pennies a gallon, we wasted it. Not much has changed.
If we had to count how many gallons of gas or how many horses that we have to pull our chariots, we wouldn't know. Even people who are very concerned about the environment and very in tune with the energy issues of the day have very little idea of what they personally consume.
And since the 1970s, as a nation, we've consumed more energy than we've produced. Most of it goes to transportation, 41%. We use another 23% to light and heat our homes, 17% for the products we buy, and 15% for services.
Count the number of cars, and that includes the service road, both the east and westbound lanes of Highway 7.
Start.
Our nation's energy budget is out of balance. At Minnetonka High School, students are learning what that means.
Stop. Typically, high school kids are thinking about fast and speed, and they're not thinking about fuel economy, and we're trying to get them to think a little different fashion.
It's going to take a lot of new thinking to get our energy budget in balance again. These students, working as a team, are learning how to design and build a super high mileage vehicle. It's an exercise that makes them think about the technology we need to balance our energy budget.
The mileages that we get from anywhere from 200 to 350 miles per gallon, very, very exciting for the kids because they're driving now and they know what their car is getting, and they know it's expensive because it takes a big chunk out of their pocketbook.
These students have driven their 2-horsepower vehicles across Minnesota on 1 gallon of ethanol blended gas. Their families in 3 cars behind them had 400 horsepower and used about 45 gallons. And transportation at 41% is the first answer to the worksheet assignment. Name the biggest uses of energy in the U.S. We use 23% of our energy resources to light and heat our homes. 17% goes into the products we buy. Another 15% goes for services, with 4% left over. The oil and natural gas we burn are made of hydrocarbons, molecules of hydrogen and carbon. Our next story looks at the huge amounts of hydrocarbon energy we use for everything we do, how dependent we've become on hydrocarbons for even the necessities of life. Do you know how much energy it takes to get a gallon of milk to the table?
I don't know if you've ever been in a house with water.
Everything that happens takes energy. It's a fact of life, a necessity. It's so universal we don't think about it. We take it for granted. But there's energy in everything we use. Take playing a computer game. Electrical energy from burning coal. Plastics made with energy from oil. Take a factory making food products. Pump motors run by electricity from burning coal. Heat from natural gas, oil burned to transport the finished product from the plant. But these examples are obvious. Look at the power lines. In the United States, we use a lot of energy, almost all of it from fossil fuels. Every 3 days, we burn our weight in fossil fuels, oil, coal, and natural gas. Burning those fuels adds carbon dioxide to the atmosphere. 3 pounds, 30 cubic feet for every pound of fuel. How could we use that much? A simple example, like an after-school snack of milk and cookies, shows how. But where are the fossil fuels here?
Well, if you go backwards from the milk that's in your refrigerator, you've had to transport that milk from the grocery store, most likely in a vehicle, from the grocery store to your home.
At the grocery store, there's a room as big as some people's homes that's a refrigerator. It runs on electrical energy. More burning coal in a power plant. When we buy things, we're also buying energy.
But then from the grocery store, it had to go from a distributor, most likely. Before that, it was transported from maybe to a farm, to a processing, and then from the processing to the distributor and bottling company, from the bottling company then to the distributor. So there's energy in all of that entire process.
Now you can understand how we've become hydrocarbon humans. Fossil fuels are so rich in energy and such a big part of our industrial food system that the energy it takes to produce our food is 10 times greater than the energy we get out of the food itself. The worksheet assignment is to complete these sentences. In the U.S., we burn our weight in fossil fuels every 3 days. Burning 1 pound of fuel releases 3.0 pounds of carbon dioxide with a volume of 30 cubic feet. So the worksheet answers are 3, 3.0, and 30. Well, if we're using that much fossil fuel to do the simplest things and we're changing the atmosphere and we're running out, what are we going to do? To figure that out, we need to understand how energy itself works. Our next story looks at the one-way law of nature that governs energy. It's as familiar as hot coffee cools, it never gets warmer. A child on a swing comes to rest unless you pump or get a push. The law is, unless you add energy to a system, it's downhill all the way.
Is that just from the heat?
Ah, hot coffee. With an infrared camera, you can see its heat energy. Here you see a body's heat energy slowly leave a chair. It's cooling down, a small example of a law of nature. If you don't add energy, warm things always cool down.
That's not leaking so bad on that door there.
Workers from the Ramsey Action Program use an infrared or thermal camera to see why a house is cooling down so fast. Heat energy added to the house by burning natural gas is leaking out.
Thermodynamics has a law, the second law, that says everything runs down. So all of our stored energy is always running down. And if you go down in your basement and look in the furnace or in the water heater if you have natural gas, you'll see this little flame.
Millions of little flames, thousands of square miles of city surfaces, hundreds and hundreds of smokestacks, millions of automobiles, and we have urban heat islands. That's a 5-degree temperature difference between cities and the countryside, visible from satellites.
We're using heat from the turbine that would otherwise be wasted to the atmosphere through a cooling tower.
The municipal power plant in Wilmer was the first one in Minnesota to slow the process of turning fossil fuel energy into thermal pollution.
It is heating water, which is then being pumped throughout the city to various buildings, homes, businesses, government buildings, and to heat those buildings with that water. It's a good example of how systems can be used together to more efficiently use our natural resources.
Stored energy resources always become less useful after they do work. That's called entropy, a measure of the order and energy in systems.
How does this reuse energy? Is there any way we can?
Kids are going to have to learn how to design the kinds of things, whether it's cars or houses or food growing systems or electrical generation, that lives on our budget. Instead of fire, we're going to have to learn how to use the sun directly.
Changing to solar-based renewable energy from fire-based fossil fuel energy will take lots of new construction and more conservation. The power plant in Wilmer is a good example of conservation. It's been generating electricity and district heat called cogeneration since 1913. So people there can get electricity and heat while most power plants just make electricity and waste the heat. That's efficiency. Using stored energy as many times as you can to do as much work as it can while it's running down. The worksheet assignment is to complete these sentences about the law of nature that governs stored energy. Stored energy always becomes less useful each time we use it. That is, each time it does work. It's called entropy. So the worksheet answers are stored, less useful, and entropy. The laws of thermodynamics, that's the movement of heat energy, can help us design renewable energy systems that match energy needs to energy resources, so we can live on our income from the sun. Our next stories look at the two main renewable energy strategies called active and passive solar energy. We turn first to the challenges we face with active solar, capturing and storing the sun's energy ourselves. During the Civil War, Minnesotans had an energy problem, a food energy problem. Most of the sugar they needed came from the South. So farmers grew sorghum, a plant like sugarcane. They squeezed out the sweet juice, boiled off the water, and made molasses.
How does it taste?
Minnesotans have an energy problem today. Our nation is using up its liquid fossil fuels, and we don't want to quit. They're powerful, reliable, and easy to use. Speaking practically, we're addicted. Every day over the United States, the sun sends us 500 times as much energy as we consume.
What we have to be able to do is to figure out ways to gather that solar energy and to store it so that it is available when we want it and in the quantities that we want it.
Collecting and storing solar energy is the special talent of plants. Farmers know how to gather plants like this sweet white lupin, but we humans don't know how to gather solar energy directly very well yet. Farmers turn corn into a liquid fuel called ethanol at this plant in Marshall. It takes a lot of energy to grow and process corn, and some say more energy than we get out of it. Systems for collecting and storing infrared heat from the sun have become more common in recent years as the cost of fossil fuels increases. A black surface absorbs the heat and warms a fluid. It transfers the heat to the water or air in the house.
The light is being turned into an electrical current, which...
In a lab at Mankato State University, students experiment with photovoltaic or solar cells. The cells capture the sun's energy and turn it directly into electricity.
This is the boat that I built, and it's a small kayak with a wooden frame. And here's a photovoltaic solar panel, and that charges up the battery.
Manufacturing the cells and storing energy in batteries has a downside: toxic pollution. But solar cells are getting less expensive and more common. Fun projects like this boat give us more knowledge to capture the sun. Using solar energy immediately like Brian does in his boat is easy. Storing it so we can use it when the sun's not shining isn't so easy. Can you list 4 of the challenges we have to meet to use solar energy directly? The answers for the worksheet are storage, the biggest problem, toxics, mainly from the battery systems that we use for storage today, our lack of knowledge, and practically speaking, our addiction to fossil fuel energy. Now, if you think that's a little too strong, try going without fossil fuel energy for a day. Our next story turns to passive solar energy. That's the strategy of cooperating with the sun, taking what it gives and making the most energy efficient use of it. We visit a house designed that way that's reduced its fossil fuel use dramatically. Cooperating with nature is a strategy that's as old as sailing. Wind is one form of solar energy that humans learned to cooperate with early in their history.
There's a winch over there.
From the moment sailors get near the water, they're in tune with the elements. They live by Mother Nature's laws. Sailors take what she gives them and make the most of it. From the street, the Widman family's home in Egan looks like an ordinary house. But look a little closer. It takes the weather we get in Minnesota and makes the most of it. A house that gathers and conserves the sun's energy on purpose is using passive solar energy.
All right, a passive house has to rely on how it's oriented to the sun, because the house itself is going to collect the heat. So it has to look as much at the sun as possible and have as many windows as it can to the south.
Then, looking through a chart of the sun's path across the sky, the architect sees that nothing will shade the south wall in winter. A wide overhang keeps the sun from overheating the house in summer.
The normal wall with a door jamb is this thick. So here's the extra 3 or 4 inches that is insulation in this house. The wall and also
once the sun's heat is in the house, extra insulation keeps it in. Tight-fitting shutters make sure it stays in at night.
And yes, the house is more comfortable to live in, and I like having warm floors. And I really enjoy not hearing the boiler running at all hours and all days.
Every Minnesota home needs protection from the cold winter winds to keep from losing heat. Planting evergreen trees northwest of the house will change the winds so the house uses less energy. And in summer, trees on the west side of the house block the afternoon sun. Creating microclimates of trees around our homes will reduce our energy needs.
A basic function of this windbreak here is energy conservation, because it eliminates a lot of snow from getting into the neighborhood, so they don't have to plow the streets as much, people don't have to shovel snow as much. It also will break the wind in order to keep this part of town a little warmer.
Planting and building to make the most of what nature gives us will help balance our energy budget. In the 1970s, Sweden voted to stop relying on nuclear power. To save enough energy to do it, it passed laws that required homes be built to strict energy efficiency standards. The passive solar home we saw uses only 1/3 as much natural gas as the average home in the Twin Cities. The worksheet assignment is to name the ways our homes and cities can cooperate with the sun. The answers are: orient the site, face new buildings toward the south, insulate, especially important in older homes too, create microclimates, plantings around homes that shelter and shade, and plant windbreaks to conserve energy in winter. Now, we Minnesotans are proud of our state's beauty, its natural resources, but we don't have any fossil fuels, so we're an energy-poor state? Not exactly. We have lots of renewable energy, most of it wind power. We can make enough electrical energy from the wind to sell it, and we're starting to build the windmills. For 1,500 years, windmills have been grinding grain or pumping water, making their owners rich. Wind power is a renewable energy path to wealth. The fuel is free and practically infinite. Today's windmills run motors called turbines that generate electricity.
Wind turbines have been labeled the oil wells of the 90s because they kind of look like one in essence, and they produce energy. But the big difference is that it's non-depleting and it's renewable, and there's no after effects. What are we looking at? Okay, this is what we call a wind farm. In a wind farm, what these things do is we take the wind and we turn the wind into electricity.
In Marshall, you can see the largest wind farm on the Great Plains. These 5 turbines generate 1 million watts of electricity, enough for 150 homes.
There's a big computer inside each windmill that tells the windmill what to do, what direction the wind is out of, how fast the wind is blowing, how much energy is the windmill producing at any given time.
Minnesota has huge wind energy resources, especially on Buffalo Ridge in southwestern Minnesota. NSP plans to put hundreds of turbines there during the next 10 years. It has a pilot project already.
From 1980, when we started this program, costs have come down over a factor of 3 and are projected to continue to come down in the future.
Wind farms just on top of Buffalo Ridge could supply as much electricity as Minnesotans use in a year. The total energy we could generate from the wind in Minnesota is 14 times more than we use.
Wind power is clean, it's inexhaustible, it's renewable, it's labor intensive. It creates jobs in areas where there's really nothing else going on.
Except nature's wind, that is. Minnesota's wind resources could give us energy to export.
The Midwest has been called the Saudi Arabia of wind power, and wind energy can fit into the mix just like any other natural resource, and the technology has matured now to the point where it's there, and we just need to make a social commitment to do it.
Storing energy from wind to use when it's not blowing is the challenge. But with turbines on the power grid, we can trade electricity like we do now with regions where the wind is blowing. The worksheet assignment is to answer 2 questions. How much wind energy could we harness in Minnesota, and where is the windiest place? Well, the answers are we could generate 14 times our annual use, and the best spot is on top of Buffalo Ridge. So the answers are 14 times and Buffalo Ridge. Now we turn to the large-scale projects that are lighting the path from fossil fuels to solar energy. We meet a Minnesotan who helped design a power plant in California called Solar One. It uses mirrors to focus the rays of the sun, the same process used around the world to cook food with heat from the sun.
It still needs about 10-15 more minutes left of us.
Students at Roseville Junior High are learning to cook without fire. A concave mirror focuses the rays of the sun on a black tube. It gets hot enough to cook hot dogs. It's the same solar heat engineers use to make steam in this electrical power plant.
Solar One operated for Southern California Edison for almost 10 years at 10 megawatts of output, which is enough for a fair-sized community, with a higher reliability than the nuclear power plants that Southern California Edison was running at the same time.
Don Anderson was on the team that designed Solar One. He lives near Northfield now in a passive solar home that doesn't burn any fossil fuels for heat.
Now, the primary furnace is this huge window area that we have on the south face.
The Andersons live on their daily solar income. As more people do that, we'll buy time to develop our renewable energy technologies.
We have enough time, but not too much time, to start building capacity to kind of come up with other ways to source our energy. Solar energy can provide all of the energy that mankind needs.
Our challenge is to raise the use of renewables and lower our consumption, so they meet about the same time our oil and gas run out. To build a sustainable society, we have to match each renewable resource with its most efficient use.
In some cases, the appropriate technology is high technology, using computers to track thousands of mirrors on a boiler. In other cases, it's as simple as growing trees and harvesting them just as you harvest hay in order to burn wood.
One Minnesota company has patented a way to burn fast-growing trees whole in place of coal. This hybrid tree is only 5 years old.
From this, we have the technology, we have the computer tools and everything of the sort. The next generation has to learn to work with them.
At Mankato State, students design and build a car powered by photovoltaic cells, another technology people are trying to perfect. In Minnesota, our best solar resource is wind power. At Altamont Pass in California, 7,000 turbines produce enough electricity for 1 million people. There, we can see what Buffalo Ridge could look like someday. In Minnesota, in 1992, about 5% of our energy came from renewable resources. Most of that, over half, is firewood. It's a number that's sure to grow in coming years. Can you name 4 renewable energy strategies for replacing our fossil fuels? The answers for the worksheet are solar heat, like the California power plant we featured, wind power, which Minnesota is developing, biomass, burning or converting plant material to fuel, and photovoltaics, converting the sun's energy to electricity directly. With our final Energy for Everyone story, we look at what each of us can do to conserve energy, to stretch out our supplies of fossil fuels while we're making the transition to renewable energy. As you watch, think think of the things you can do to conserve energy.
Unscrew this one and put this one in.
Material to fuel, and photovoltaics, converting the sun's energy to electricity directly. With our final Energy for Everyone story, we look at what each of us can do to conserve energy, to stretch out our supplies of fossil fuels while we're making the transition to renewable energy. As you watch, think of the things you can do to conserve energy.
Unscrew this one and put this one in.
Changing an incandescent to a compact fluorescent is the brightest thing we can do at home to save energy.
Something like this high-efficient light bulb, when it's used, lasts 10 times longer than a regular incandescent bulb, and it uses 1/4 of the energy.
The water heater takes more energy than any appliance in the house after the furnace, so insulate it. A simple test shows if you have a low-flow shower head, that's only 2 gallons a minute. If the water temperature is more than 120 degrees, turn the thermostat down. You'll find other thermostats in the house.
It's not always cost-effective to buy a new refrigerator, so you want to make sure the one you have is running as efficiently as it can. Cleaning the coils is a big thing, and also cleaning the gasket and making sure that it's sealing well.
Ben Franklin said it best, waste not, want not. And the more fossil fuels we conserve, the more time we'll have to develop solar technologies. And there's lots of ways to waste not.
Other things are, I think, is thinking about transportation as the biggest energy waster. It's just thinking about trips that you could make either by walking or taking the bus or carpooling.
That's being efficient with fossil fuels. Machines get hot when they do work. More heat usually means more wasted energy. Cars carrying one person and jumbo jets are the least efficient ways to travel.
We have to think more creatively. We have to try to think about ways that we can save energy, still produce the same amount of work or the same product, but be able to use it more efficiently.
Getting to the solar-powered future won't be all work and no play. We'll enjoy ourselves, celebrating nature and the elements much like we do today, but the energy that powers us will last as long as the sun shines. People are conserving energy in schools and at work, too. The staff at the Science Museum worked with NSP this year, added more fluorescent lighting, and reduced its annual energy by 600,000 kilowatts. Can you name some things each of us can do to conserve energy? The answers for the worksheet are: to save transportation energy, we can walk, bike, take the bus, or share rides in a carpool. We can change incandescent lights to fluorescent lights. Check thermostats and lower them if we can. And stop waste. The Department of Public Service estimates that we waste 50% of our energy. One last thought about energy and physics. We're on the edge of a new energy era. Fossil fuels are running out. We'll have to replace them. Some of the renewable energy technologies we can use are as old as the hills. Others have yet to be invented. Some will save money, others will cost money, but changing the way we think about energy is the place to start. Thanks for joining us. I'm Mike Fairborn at Weather Center 4.